So this is the conclusion of our discussion on limits, and I'm going to just close it by looking at a few examples that kind of summarize everything that we've been talking about. So let's look at this example. We're going to find the limit as x approaches 4 of x times sine pi x plus 1/2 x squared. And with every limit, we always want to start by trying direct substitution. Maybe we need to do something more complicated, but we shouldn't just jump to that. We should always try direct substitution because it's the easiest, and if it works, then we're done. So let's go ahead and directly substitute 4 sine 4 pi plus 1/2 times 4 squared. So I happen to know, I have memorized, that sine of 4 pi is 0. So that means we get 0 here, plus 16 over 2. And that gives us a value of 8. So our limit exists, and we can get it by direct substitution. Here we have a slightly more complicated function, and once again, we're going to try direct substitution. So let's go ahead and substitute 4 over 2 minus 2 over 0. Now I already see it's not going to work, but let me just go ahead and finish this. So we get an indeterminate form, 0 over 0, and that indicates to me that the limit probably does exist. However, the direct substitution just doesn't work. So we need to rewrite this function somehow, and I am going to employ the use of multiplying by x plus 2 in the numerator and the denominator, which simplifies our function by getting rid of this fraction within a fraction. So this becomes 4 minus 2 times x plus 2, and I'm going to leave the denominator just as x times x plus 2. All right, so let's go ahead and simplify this. The limit as x approaches 0 of 4 minus 2x minus 4 over x plus 2. The limit as x approaches 0 of these 4's cancel out, and I'm left with negative 2x over x times x plus 2, and these x's now cancel out. So I get the limit as x approaches 0 of negative 2 over x plus 2, which is quite nice because now I can directly substitute. Negative 2 over 0 plus 2 is negative 2 over 2, which is negative 1. And there's my limit. So let's try and find the limit as x approaches 5 of this function. So I'm going to first try direct substitution. So I get 25 plus 20 plus 3 over 25 minus 10 minus 15, which is 48 over 0, which doesn't work. It's not an indeterminate form, it's just undefined. And so that indicates to me that the limit probably doesn't exist, but I want to confirm this. So I'm going to factor the numerator and the denominator. So this is the limit as x approaches 5 of x plus 3 times x plus 1 over x minus 5 times x plus 3. So the x plus 3 factors cancel out, and we can't simplify any further. And direct substitution still gives me 6 over 0. So from this, I would conclude that the limit does not exist. And I would confirm this by looking at a table or a graph. And this actually makes sense because I know that if I don't cancel out these factors, so my x minus 5 remains in my function, that means it's going to be a vertical asymptote. So I know I actually have unbounded behavior. And so if I graph it at x equals 5, the function looks something like this. So I do have, in fact, unbounded behavior. There is a vertical asymptote. I can't actually say that the limit is infinity or negative infinity because on the left it goes to negative infinity, but from the right it goes to positive infinity. So I can't provide that extra piece of information. All I can do is say that the limit does not exist. So here we have the same function, but now we're going to take the limit as x goes to infinity. And we're going to use both methods for finding limits at infinity. First, I'm just going to use the horizontal asymptote rules. Now, since the numerator and the denominator have the same degree, the horizontal asymptote is y equals a over b, where a and b are the leading coefficients. And in this case, it's just 1 over 1, which is 1. So the limit as x goes to infinity should be equal to 1. And let's confirm this by using our analytical methods, which means dividing both the numerator and the denominator by the highest power of x from the denominator. So the highest power of x from the denominator is x squared. So this becomes the limit as x approaches infinity of x squared plus 4x plus 3 over x squared all over x squared minus 2x minus 15 all over x squared. So let's proceed to simplify. 1 plus 4 over x plus 3 over x squared all over 1 minus 2 over x minus 15 over x squared. And we can directly substitute now. If we substitute infinity in for all these x's, we get 1 plus 0 over 1 minus 0, which is 1 over 1, which is in fact 1. So either method, our horizontal asymptote rule or our properties of limits, either way, we get the same answer.